In this video, we're going to take a look at a sample problem involving stoichiometric rate relationships. So what we're going to do first is we're going to write a rate relationship for the chemical equation written over here. So we have this reaction here, and the question says write stoichiometric rate relationships between products and reactants. So all we're going to do is we're going to write rate relationships that equate all these components together. We're going to start off with our reactant. A reactant, remember, we'll expect a negative number. So to make it not negative, we put a negative in the front. So we'll have negative, and then we're simply going to put 1 over the coefficient there. So negative 1/2 of the change in the concentration of N2O5 will over the change in time, delta T, is going to be equal to so now we're in the product side now, so we don't need any more negative signs. 1/4 of the change of the concentration of NO2 over the change in time, which is going to be equal to, there's no coefficient there, so 1. You don't really have to put that, but I'll put it anyways just to show you that we're not putting any. There is a coefficient. It's a 1, but it's 1 over 1, so it's equal to 1. So change in the concentration of O2 over change in time. So what this essentially means is that the O2 is produced at 1/4 of the rate of the NO2. And it also means the O2 is produced at half the rate that the N2O5 is consumed at. And you can compare various components that way. So we wrote our rate relationships here for that particular equation. That was our first step. And that's based on stoichiometric coefficients. So now our next question in part B is if the rate of disappearance of N2O5 is this at 60 seconds, so it's an instantaneous rate, determine the rate of appearance of oxygen at this point in time. So we want to find what the rate of appearance of oxygen is at that point in time. So here's what we know. We are going to be comparing the N2O5 to the oxygen. And what we know from our relationships that we built there is that the rate of oxygen production, I'm going to write rate of oxygen production, is going to be equal to -1/2 of the rate of NO2 consumption. So we know the rate of N2O5 consumption to be this over here. Now, because it's being consumed, this is technically a negative number. So what we're going to do is we're going to rewrite this as the rate of oxygen consumption is equal to -1/2 times -5.6 times 10 to the power of -2, and then the units are the same. I'm not going to write them there. I'll write them at the end. So we're going to have -0.5 or -1/2 times the 5.6 times 10 to the power of -2, and we're going to get -0.028, and that's going to be moles, not negative, sorry, positive, because it's being produced. 0.028 moles per liters second. And if you want to do 1 sig fig because of the time, you could there as well and get 0.03 moles per liter second. And that would be the rate of oxygen production. Another way you could have done this, if you did not write the rate relationships there, is by simply doing a mole ratio. You did a mole ratio here, technically speaking, just using the relationship you wrote above. So all you could have done is just take a look at your ratio between the N2O5 to oxygen, 1O2. And if the rate of disappearance for this is 5.6 times 10 to the power of -2, then to get to oxygen, you simply have to divide by 2 because it's a 2-to-1 ratio. So it's just like regular stoichiometry. And in the end, you'd get the same answer over here as well when you do your rounding. So 0.03 moles liters second. Again, the reason I had the negative here is because technically speaking, this is negative as well, since we have a disappearance happening. So that negative really controls for the fact that you have a negative number there and makes your answer positive in the end. Typically, we report our answers as positive numbers, but it's understood that if something's disappearing, you'll calculate it as a negative number, especially when you're first doing your graph. So let's go try the part C. Calculate the rate of appearance of NO2 at 90 seconds if the rate of appearance of oxygen at this time is 2 times 10 to the power of negative 2 moles per liter second. So now we are comparing the NO2 to the O2. So we're doing a different comparison here. We're doing this one to this one in green over here. So here's what we know. We know that the rate of oxygen appearance is equal to a quarter of the rate of NO2 appearance. And so we want to find what the rate of the NO2 appearance is at 90 seconds, so an instantaneous one. And we have the rate of oxygen production. So essentially we're trying to isolate for the rate of NO2. So this 1/4 here, it's 1 over 4. When you send it to the other side, it becomes a multiplication. So what we get here is that the rate of NO2 is equal to 4 times the rate of O2. Right? If the rate of O2 is a quarter of NO2, then NO2, to find that, you have to do 4 times O2 to get your rate of NO2, since it's 4 times more. Also, stoichiometrically, it makes sense, right? It's a 4-to-1 ratio with oxygen being the 1. So you're multiplying by 4 to get your NO2 from oxygen. So that means that we're going to get 4 times the 2.0 times 10 to the power of negative 2 moles liters seconds. So we're going to go ahead and do that. So 2 times 10 to the power of negative 2 times 4 gives us 0.08 moles liters second. And that makes sense, 1 sig fig there because of that 90 seconds there. I will tell you if that is considered a real significant figure. Again, it depends on what graph we're looking at. But in general, just to be safe, go with that's 1 significant figure. So we had 0.08 moles liters second as the rate of appearance of nitrogen dioxide, which makes sense because it is 4 times that of the rate of appearance of oxygen according to our stoichiometry coefficient. So essentially, when you get a problem like this, like B or C, even if you're not told to make stoichiometric relationships, you should build those first and then just choose the ones you need to compare in the question. So in B, I had to compare the N2O5 to the O2, but in C, I had to compare the NO2 to the O2. And so you just kind of choose your parts that you need, put them in, plug your numbers in, isolate for what you need, and there you go, you get your final rate with respect to the other substance. So that is using stoichiometric relationships to determine instantaneous or average in some situation rates of reactions with respect to different substances in your reaction.